Yeah, again, thank you to be here for the lecture of today. We will restart with a few issues related to the trigonometry functions. I will repeat it shortly. I will simulate because I think we didn't simulate with trigonometry functions. I will point it out. I will point out some important aspects, and then we will start with the non-convex optimization problems using a solver. The name is particle swarm optimization method, the methods. We will see one method, but I will dedicate a couple lectures, 2 or 3 lectures. Uh, Nevertheless, I will show you possible variations. Here in Loifana, we worked a lot with the PSO, also considering our own variations in the sense. Okay, let me reopen. The mouse doesn't work. This is also another interesting thing. Okay, let me open the lecture of last time, showing just the last slide. The first is the last. Up. Let me share. The first is this one, inspiring lecture on fitting problems using trigonometric functions. As I told you, we can use any kind of family of functions. We analyze in depth the polynomial functions. Now I would like to present another one, the trigonometric function, but of course, we can consider also exponential functions. We can mix also different functions. And the problem remains the same. How I can choose a regressor with respect to another one, a family with respect to another one. Or if I, with my fantasy, I combine trigonometric exponential polynomial. We did in some projects. How I can choose what is the best one. The criteria which we have seen in this course is the R-square adjusted, but is not the unique one. The idea is to show you that in any case we need and the criterion, sometimes more than one. I don't have time to analyze more complex decision criteria. But in any case, we understood that we need an appropriate, let me say, appropriate cost function, because you remember I compare R squared with R square adjusted. And we have seen that R square adjusted is a cost function with minimized both deterministic and statistic one. We have seen many aspects of this. Yeah, at the end of last time, we concluded this lecture here, considering this comparison between my polynomial function. Here you can imagine this as a sum of elements. If you think we can see here as a sum of k starting from 0 up to n of ak multiply x up to n minus k. We can see the sequence. If you want to compare formally with this one. This is also in the sum. Anyway, these two regressors, basically, they have many similarity in the sense that we have elements, and the sum is the Fourier analysis I told you last time. But the similarity we have also here, let me say, in the parameter n, which states the number of coefficients. Until now, starting from now, I would like to say, we will speak about, also last time, number of parameters. This is our criteria. Remember, Last time we have seen between the polynomial number 3 and the polynomial number 4, we had in number 3 the best. The polynomial number 3 was polynomial order 3, something like that. We have the best square adjusted, the minimum, and the minimal number of coefficients, because polynomial order 3, we have 4 coefficients. Ideally, we look for always the minimal square adjusted, because it's a compromise between deterministic statistic error with the minimal coefficients. Of course, it could happen that we have a minimal square adjusted, but not the minimal coefficient, because the problem is not convex in terms of n. Do you remember? In terms of n, which is the maximal number of coefficients, coefficients n plus 1. But in any case, n is the responsible for the number of coefficients. With respect to n, R square adjusted is a non-convex. If you choose F square adjusted, the problem is non-convex. This means we have a more than 1 minimum. Here, n is also here present. The coefficients here is not exactly n plus 1, but 2n. 2 multiply n plus 1. We can see here plus 1 is here. Why 2 multiply n? Because we have a sine and cosine. This does not mean that given a set of data, here we have more coefficients than here. It depends on the data. This is very important to be understood. Even though here the number of coefficients is 2n plus 1, and here is just n plus 1, not necessarily the coefficient which we need to approximate data are larger than this one. Why that? Because this is an optimization process. It could be that we need a few a few parameters here when we need less parameter than this one. If in the data I can see the periodicity. If I see something which is repeated, or if I am able to build in a repetition, of course, here I need a few parameters. I don't know if you remember Fourier analysis and so on. We can approximate with a few parameters in a function if the function is a periodic one. Because this is the sum of periodic functions, and if you remember, a sum of periodic functions is again a periodic function. This means it could be suitable, even though structurally it seems to be that we have a more parameter formally, I would like to say. But in the context of approximation inside an optimization problem, it could be that we need less parameter using this regressor here than this one. And we hope that we have also the minimal square adjusted. Of course, if this is not the case, typically the priority is the minimal number of parameter, minimal number of parameter. Of course, nevertheless, a square adjusted should be a relative small in this sense. Analyzing here, we have coefficients to be calculated. Then we have an interesting k is also here present, if you want. No? If you think about the sum of k starting from 0 up to n of k, which multiply x up to n minus k, we have also the index k also here, which is a parameter which states basically the number of the element which we have in the regressor. N, the maximal number, also here in this context, is typically a parameter to be optimized, like here. We can see in this representation. I come on this representation again. Very interesting, this T. T represents the period which we can see in the data, which we can see. Please pay attention. We will come back on this expression, which we can see in the data. Because typically we don't have a period, we have the data. But now with the simulation, with the MATLAB, I will clarify the meaning which we can see, which it can be modeled, which it can be represented. let me see if I forgot to say uh, something. I don't think so. Mm. Okay, I think we can start to analyze this again, these two expressions. We can see here this expression which I told you many times in different form. This expression here is an expression quite similar in which we can see again this exploration matrix, the coefficient which must be calculated, we can call again this column here theta, which we can see 2n, 2 times n plus 1 coefficients, but not necessarily this 2 times n plus 1 out more than this one. This depends on the data. No? Of course, it depends also on the function which we want to minimize. Once is given, a square adjusted is one example, and we have to calculate the number, and which one, of course, the number of coefficients which minimize a square adjusted. This is absolutely the same. But here, the problem which we have is the same like here. If I have to minimize, to find the optimum, better to say, with respect to n, is a non-convex problem, definitively, because we cannot separate what I know with what I don't know. The same concept with t. T is a period, is a parameter which must be optimized. Because now we will understand better, because this is also, this periodicity in the data is in a model, in a way to think about it, the data. It's not necessarily we can see directly a period in the data. Let me go in depth on this representation, on some possible problems, and then I will show you a couple of simulations, then we will consider the PSO, which allows to solve this kind of problem, basically to determine the maximal number of k, this means n, the maximal k, this means n, and also t. Again, if t is not given, if n is not given, typically it's not. The problem is complex. We can do as last time, try and error, but if typically we use in a solver, we use a method which is let me say, oriented to the non-convex optimization problem, and a structured method, the program in this sense, to calculate nt, and the corresponding, after that, A0, B1, A1, and so on. I mean, the parameter to be optimized are T, N, and all these parameters here. But to do that, we need methods which allows to do that. One of them is this PSO, particle swarm optimization method. Before speaking about PSO, let me go in depth on this. Do you remember last time I scared you with this slide, which I represent or repropose today? Yeah, again, in a non-convex optimization problem, the parameter to be optimized at T, N, the maximal, and the corresponding coefficients A0, A1, A B1, A1 until Bn, An. Yeah, 1 second. You remember this? Let me. Let me organize it a bit better in order to show you how we can be. Right. This is the regressor. Assuming that t is given. Can be chosen is better because typically it isn't a parameter to be considered in optimization problem. But anyway, at this moment, t is given. What is this? Is exactly what we did. What we did in case of polynomial. I mean, I calculate y hat at point x1, in this case, using this regressor. This regressor is formally different with respect to polynomial structure, but I can calculate for n elements, or better to say 2n element, 2 times n element, this expression at the exploration points x1. We can see here x1, 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 x1 everywhere. For what? For k equal 1, for sinus, for k equal 1, for cosine, and then k equal 2, we can see here, k equal 2, sine and cosine, and so on until k equal n. Everything calculated for the point of the exploration variable x1. Exactly what we did for the polynomial. This is circa y1. We want to approximate this time using another form. Please pay attention. We can mix also, no, polynomial this one and this. How we can choose? Okay, again with the concept of a square adjusted. Consider the minimum of a square adjusted, hopefully with the minimum of coefficients. But anyway, we can find nevertheless a compromise between. And I do the same for x2. This means I approximate the measurement of y2 using, again, this regressor here. And then formally means to calculate this expression here at the exploration point, let me say, of the variable x2. It's the same expression. Instead of x1, I have x2, as we did for the polynomial. This is easy, no? What is unknown is a0, a1, b1, and so on until bn, until an, bn. Or if you want, bn, an. If I do the same calculation until the m exploration variable and, of course, the measurement m, we have basically what we did here. Anyway, we have an expression of m equations, which looks like something like that. We have m equation and 2 multiply n plus 1 parameters to be calculated. Now, we can understand this apparently complex expression better, I hope, because these elements here can be vectorialized as we did for the polynomial. No, it's absolutely not different. Here we can, if we want to use, we can use this least square in the form which I presented, localize the parameters in this vector here. When I can use, if everything here inside is known. This means t must be given, n must be given. It's not the general problem, therefore we need a solver, we need another method, because the least square, if here inside we have we mix what I know with what I don't know, we cannot solve. We have a seen many times with the examples of last week. But it's clear that row multiply column, I will have this information here for the first product row multiply column. For the second, if I do this row multiply this column, if you remember the rules, the product between the matrix and vector, I will obtain this expression here, and so on. This means if everything here is known, in particular, if t is given, n is given, I can use again the least square. Basically, if I am a little bit, if I don't think about what happens inside, no difference when I build the data. Before showing you another interesting problem, I will simulate a little bit so we can relax, we can repeat everything, and then we will conclude this part with some problems which occur, nevertheless, with the using trigonometric functions. Let me open MATLAB. I will upload the material at the end of the lecture. Let me open MATLAB. Because last time I didn't tell you about MATLAB. No? We didn't simulate, I think. 1 second, because MATLAB takes a little bit time to start, and then we will go in depth on this a little bit, I would like to show some possible problems which can be in the presence of trigonometry function, which can appear in the presence of trigonometry function. Okay. Let me share. I will upload later this program, which you can see here in this M file. Clear all we know, close all we know. No? Clear all, I cancel every variable which I have here, if I have. Is just prophylax. No? This is not essential, but typically we do. Close all, we close the windows, the figures, better to say, which we have. Look at this now. We have this vector exploration variable, and this is the corresponding measurements. Let me consider this T, and this is the trigonometric exploration, or better to say, the exploration matrix based on the trigonometric functions, in which we are considering just k equal to, we can see here, 1 with multiply x1 sine, 1 with multiply x1. x1 is the first element of the exploration vector. And then we have here 2 times, which multiply x1, and 2 times, this for sine, which multiply x1 for cosine. This means, just to understand a little bit, to have a little bit of feeling, we have just n equal to, or k if you want, until 2. You can see that, as I told you now, we build the row of this matrix considering all elements of the exploration vector. You have x2 here, x3, x4, exactly as I tried to explain before. The rest of the program does not change. I mean, the solution is always the same, assuming that t is given, assuming that the maximal number n is given. Otherwise, we cannot apply this. Or we can apply heuristically, as last time, try and error. We will see today how we can solve a non-convex optimization problem in a possible solution. How many solvers we have? A lot. But almost all is based on let me say, directly or indirectly using this gradient principle. I don't know if you heard about that. I will tell you. Anyway, this is the solution which we know. Now I change just a little bit the name. Remember, here we have xtr because trigonometry, before we had x5, x4, depending, or x3, depending of the order of the polynomial. But the structure is the same. Inverse of x transpose multiply x, multiply x transpose, multiply y. Remember, this we calculated, I flesh out also a little bit the demonstration. Then the rest is exactly the same, in which we have here a new vector in order to represent. Here is the regressor. Here is the regressor, which we have calculating in its domain. Each element of X is in a vector here to represent inside the sign, but should be inside cosine, inside all sine and cosine of the sequence. The rest does not change this formula. Here, I calculate just R squared. If you want to do at home, if we decide to consider the project in this context, we can modify here to remember using m minus 1. I have to define m divided m minus p, which in our case is 2 times n plus 1. To obtain the R square adjusted. I didn't put, but we did the last time. It does not change. Let me show you what happens now. I am considering here just R square because I would like to show you something interesting in this context here. But try to do, or we can do in a project together, and the problem, or but okay, this more or less is in this sense is more in a project than in a lecture. But I think you can figure out what I intend. Look at this. We have R square adjusted relative low. Relative is a good word. But if you remember, R square adjusted, excuse me, R square, we don't have R square adjusted. R square is an indicator which can be used to calculate theta 1, theta 2, basically the parameters, but we cannot use in general, because with respect to the number of the parameter, this is the key point, is not convex. But in general, we know that very low value of R squared indicates very large deterministic error. Do you remember this? In fact, if you look what happens here, we can see that between, for instance, this point and this point, a possible approximation is around minus, I mean, very far away. This means also optically, it seems that I cannot really trust optically this possible approximation, because again, we have to find a compromise between the deterministic and stochastic one. Here it seems to be not really a compromise, because the deterministic error, it seems to be in accordance with the value which we have, too large, because it's too few, it's too low, the value of R squared. Why this appear or happens? Let me come back on the picture. Let me share. The period which we fixed is equal 8, if I remember well, 4 multiplied 2. No? This means starting from here, I will have again the period. But it seems that probably we have too few points in a possible period. I mean, what I am assuming here is that starting from 8, I will obtain the same measurements. Of course, we don't have the measurement. This means it's an assumption. Why this assumption is too conservative? Because, of course, we don't have value what is the maximal value, which we have here. Let me show you. We are assuming that this value here is periodical with period 8. But of course, we cannot really justify this because we have just one value after 8, and this one is. I cannot say from this element here that this value will be repeated. Basically, we can reformulate thinking that we have too few values inside the period. What we can do that? If you increase t, for instance, let me write 10. Now, we have here a value which says that the deterministic error is relatively small. Let me show the solution graphically. We can see that the approximation, the deterministic approximation, is quite, let me say, good. I cannot say if we can see it, if this is exactly what we want. Again, what we want should include also n. Do you remember? I told you a lot. But in any case, we can justify that the deterministic error is relatively small. Why that? Because I am assuming that somewhere, let me say, far away, the data will be repeated. This means inside the domain of my measurements, I don't see the period or the periodicity of the data, but far away, I assume, far away from my domain, I will assume that the data will be repeated. This is how possible to say. Let me show you a little bit better with the representation. I will assume, let me consider 2 periods. Yeah. Now I'm considering 2 periods. We can see that starting from 40, I have again the function. Basically, is the period is 40. This means I concentrate my approximation in a few part of of my regressor, in which the periodicity is not possible to be seen. But I assume that somewhere far away, the data are periodical. In this case, in this sense, I can approximate at least the deterministic part, or I can reduce the deterministic error. And of course, this is just a part of the problem, but it seems to be possible in this sense to do that. Let me see if I can explain a little bit better. Let me share, because probably I didn't share. What I'm doing here, yeah. Excuse me, I didn't see. This is it, what I would like to show you, because I am considering that I will repeat my data starting from here. This means I will use just a small part of sine and cosine function to approximate my domain or my data. what is the problem which we have, so we can clarify better? Let me show you one slide, and then we will come back on this. It seems to be, nevertheless, that the trick is to use in a period large enough. Problem is how large? We will answer later, but before answering this question, I would like to clarify why at the beginning we had a relative bad representation in terms of deterministic error. This is the definition of a periodical function. This means starting from t, I will reassume the same values. This is probably you know this definition. F of x is equal to f of x plus t. T is the period. This means for x larger than or equal t, we have the same values. No? Basically. Look, what I show you now is exactly this case here. We have two trigonometric functions. I consider here just sine. I consider here just sine. But of course, the same considerations can be done if I take into account cosine. Let me consider just sine. We have two sine. One with period t and one with period t divided 2. The blau. The blue line is the period of this is t divided 2. Half of red, no, it's clear. K equal 1, red, and K equal to blue. Look. Now, probably before showing this, let me show you half of a slide. Here is clear, no? We have two frequency, two period, if you want. Let me show half of the slides. Because probably you don't remember the famous theorem. The name is Shannon theorem. This must be considered. So I will repeat this for you. Just a repetition of the chapter is Introduction to MATLAB, because in another course, yeah, this kind of problems they are inside of a pseudo MATLAB course. Look at this Shannon theorem. Look at this picture here. Just a few words, no? Because it's not exactly the goal of the lecture. Here, I don't want to approximate, but the problem remains valid in an approximation. Yeah, I fit totally. In our case, we want to approximate, but the problem remains. Look, we have this measurements. We have 4 data, and I want to meet exactly these 4 data. For instance, look, with these 4 data, it seems to be that you have 2 possible solutions. Probably you have also more than 2. But in any case, it seems to be that graphically we have 2 possible solutions. Why we have these 2 possible solutions? We have these 2 possible solutions because, I don't know if you remember this theorem here, because we don't respect this condition, which says that the sample time is the distance in time between the point, assuming that we have a constant, yes, to understand, should be less than t divided 2. Or equivalently, t, which is the period of the approximating, let me say, the function, larger than 2 times ts. This means for each period t, I have to consider at least more than 2 points. But this is not the case. If you think, for instance, in the green, excuse me, in the red. We have just 2 points. This means if this is not guaranteed, this or this is the same condition, we have this problem, which allows to say it is not possible to see which one will fit or will meet in our case, in the case which I presented this point. This is an insufficient condition. This means could be also violated, but in general, if it's not guaranteed, we can have this kind of problems. And also in our approximation must be respected. This means T of our, let me say, approximated function must be larger than 2Ts. Now, in our case, we have not only one T, we have a T and T divided 2. This means typically we consider the more, let me say, conservative solution or condition. This means we consider T divided 2 larger than 2 times Ts. Because if T divided 2 is larger than 2 times Ts, also T is larger than 2 divided Ts. This means T larger than 4 Ts. The other problem which we have is that Ts is not constant. In sense more conservative, we are considering the larger Ts which we have. I don't know if it's clear what I intend. This is a theoretical theorem which say we have points we want to meet with one harmonics. We have Ts constant, and this harmonic must be in a period larger than 2 times Ts. Now, if we have a series of harmonic, of course, we can consider which one the fastest. This means the harmonic which is smallest period. In our case, in our example, we have a T divided 2 larger than 2 Ts. This means T larger than 2 Ts. Of course, this is conservative, extremely. In any case, if it's guaranteed, we can reconstruct the signal. We can calculate, let me see, univocally the function which meet all points, or univocally the approximated regressor univocally, because the problem is convex, must be convex in the sense. The other problem which we have is very often Ts is not constant, like here. The distance here, Ts1, Ts2, they are constant in the formulation of the theorem. The theorem is in sufficient conditions. Let me now come back here. We have two frequencies, let me say, two functions. And of course, now, in accordance with the, as I told you, of the Shannon theorem, we will consider not T, but T divided 2 multiply 1 divided 2, which is conservative. I clarify because I am considered the fastest one. If it's valid for the fastest one, it's valid also for the slowest one. The other condition which I have to consider is the large Ts, because it could happen that the values, we called this the exploration values, they are not equidistant. They don't have the same Ts. Let me apply in my Simulink, in my MATLAB, so we can conclude this topic. Where is MATLAB? What happens here? It's exactly the case. We have here Ts equal 1 divided 5, but here Ts is 3 divided 5, right? The distance between 5 and 1 divided 5 is 3.5. And then we have 1, 1, 1. This means the maximal value of Ts is 3.5. Why I have to multiply by 4? Because I have a t divided 2 divided 2, multiply 1 divided 2, as I try to explain. This means starting from here, we start to have some problem, possible problem, as I told you, possible problem. Probably it could also work because, as I told you, it's extremely conservative part. But let me show you, and then we will condition. Let me show you what I intend exactly. I hope that I calculate well. No? 3,5 plus 1,5 is 5. And this means it's okay. Why 4? Because this is the maximal TS, the maximal distance. Why 4? Because we have two harmonics. I have to consider therefore the fastest one. In this sense, it's a conservative. This means larger than this could be possible, strictly large. With this value here could appear some problems. Why could it not necessarily appear? First of all, is in sufficient condition. Secondarily, the fastest is not guaranteed, but the slowest, nevertheless, is there. This means it could be that the approximation could be nevertheless acceptable. Let me see, but I think that will appear some small problems. Let me see. The value is not totally bad in the context of the, I mean, we cannot say anything about this because remember R squared. If you want, we can build also R square adjusted. Could be nice. Could be nice. Let me do it. I had in some other software, but now very quickly I found this. Let me define here the number. M is how many value we have? 1, 2, 3, 4, 5, 6, right? Yeah. Then we have P, as I told you, equals 2 times. Let me see how I can express here. N is 2. Excuse me, plus 1. No? Because this is, as a comment for you, is P equals 2 times N plus 1. We have two harmonics. This means here I have to multiply by M minus 1 divided M minus P, right? Multiply. Let me see. My mouse doesn't work. It's a shame. This is the values. Let me see the approximation. With zoom is always the problem. Huh? Yeah, we can see a little bit that independently on the values. Let me. Oh, I can build here. Excuse me, the mouse doesn't work today. Yeah, we cannot judge optically, but let me increase a little bit. What happens in particular in R squared adjusted and also optically. especially the mouse doesn't work today. Extremely difficult for me. Let me write here R square adjusted. Okay, let me increase values. I mean, if I decrease, we will have some problem. I show you? I don't know if I share because it's a shame. I have to do many actions for this lecture in Zoom, particularly when the mouse doesn't work. Okay, now. Yeah, look. We can realize that something doesn't work because R square adjusted must be nevertheless positive. Remember this concept. Look optically. As I told you, if you reduce this T, we can have some problems. Optically, again, we cannot realize so much, no? But also from the data, we can see that if I reduce again, we will have some problems for the reason which I clarify. The question is how I can increase. Also, this we have some limits. Again, R square adjusted, and so on. Let me try to I don't know 10. We can see that probably with respect to the square adjusted, we have some value better. This means we have an optimal period. I don't know if you realize this. Excuse me, I cannot work with this mouse. You remember was 0.22, and then if I reduced really a lot, was not acceptable because it was negative. It's too large. It could be that between 3.5 and 10, at in the middle, we have something optimal. Believe me, 0.22, and then this is increasing. But I think that we can find the minimum between 3.5 and 10. I don't know, we can try with 5. It seems to be again monotonic, but try to at home to work on this. But of course, it could be also monotonic. In this sense, this means it's possible to think that this function, trigonometric function, is not in this sense suitable for this kind of point. Make also sense because I don't see any kind of periodicity in this data. This means I have to artificially think that starting from 20 here, we have the period. But of course, we don't know. I don't see it. Let me try to test a little bit. Yeah, it seems to be in this sense, monotonic with respect to t, no? With respect to t. Again, with respect to t, this must be specified. Okay. Of course, if I increase t, we will have a different problems because look, if I do, for instance, 400, no? Just to put an exaggeration, look what happens. We have also some not meaning the reason is that this matrix becomes to be singular, because large T means sign will tend to zero, because sign of zero or something around zero or the very small is sign of very small is almost zero. This column will tend to the same value in accordance with the numerical limitation. Okay, this is a little bit everything about this. Probably in this case, I would like to say that the data are so strange that they are not periodical. Try to do ATOMO with some periodical values. No? In this sense, we will see that that value, this measurement, we will see that the approximation, square adjusted in particular, will make sense. Will make sense because we will find the convex region also with respect to T. Here, the parameters to be optimized are different. N, T, and the coefficients. This is the parameters. Okay. In non-convex optimization problem, let me open the presentation, the new presentation of a new topic. Typically, we used a method, or the method, numerical method, typically, because we don't have an analytical solution. Or if we have to limit the regions, but typically we are working directly. Do you remember that this distinction? The directly means directly using numerical methods. I would like to start introducing this a few words, this project, which we did some years ago, in which we applied this PSO. The project was basically is described very shortly in this picture, in which we tried to find optimal, again the keyword optimal velocity, in particular translational velocity and rotational velocity of the end effector and the end effect of a robot, in order to minimize the roughness of a surface. We have here in a process, we have here in a robot, which try to reduce the roughness of to reduce in the minimal sense, the roughness of a surface. This means the idea is to find the optimal angular velocity of this end effector. It's in a rotating part, but also translating. This means we can think about that we have an optimal translational velocity and an optimal angular velocity of the end effector, the phrase, for instance, to obtain the minimal and a possible minimal, because the problem is not convex, a surface of our piece. It's a milling process to improve the quality of a milling surface in terms of roughness. This is the problem. Yeah, again, it's already clarified that we can consider two possible variables to be optimized: omega, the angular velocity of this end effector, and v of t, the translation velocity. Yeah, again, about, do you remember this picture? Probably I already presented, I don't remember. In this picture, we can see, it's not exactly well done because it seems to be that here is going far away, but let me consider that I have just one minimum and just one maximum. Isn't a convex problem in terms of minimum or in terms of maximum? I mean, we have just two possible optimal solutions. If I am looking for a minimum, this is the optimal solution. If I look for a maximum, this is an optimal solution. Maximum and minimum have the same problem, basically. I mean, and the problem which can be formulated in terms of minimum can be formulated in the term of maximum. What I worked when I was young in a company, in a research center, in which the idea was to optimize the dimension of a motor. This means dimension in which sense? Dimension of the rotor, minimal number of winding, minimal number of permanent magnets. But in the meantime, maximal torque. It was a rotational machine, a rotating machine. But if you consider the cost function, force divided volume, parameterized by all dimensions, number of windings, permanent magnets. In this case, we are looking for the maximum, maximal force, minimal volume. This cost function, which is the ratio between force and volume, we are looking for the maximum. But if I consider the inversion, volume divided force, we are looking for the minimum. This means maximum and minimum could be represented with the same optimization problem in this sense. But anyway, the concept of the convexity can be this picture I already told you, I think, I don't remember. This kind of problem, if this is the function to be optimized, is not convex, because we can see many hills, many valleys. This means this is the best of the best. Of course, it could be that for me it's okay also in a local minimum, but in any case, should be nice if I am able to activate the animation. Let me see. I don't know if I shared, because I didn't share. I am sure. No, I shared. It was at the end of the lecture. Okay. Probably here. I have yeah. Look at the bottom of this slide. We can see in general here the same picture which we have in the upper part, but let me say in 2 dimensions. I mean, in which we have here the domain X and Y, or omega then V, if you think about our original problems. And this picture which you can see, they represent the level curves. I don't know if you have this concept of the level curves. Think about that this picture in the upper part can be set with parallel planes. And then try to consider the projection of this intersection in the domain. I try to clarify with the picture now. Assuming that I have something like that. Now, if I intersect this picture here with a plane parallel to X and Y, I will obtain somewhere this intersection. I don't know if it's, 1 second, you can see it. Yeah. What happens? I don't understand. With Zoom is always a problem to understand what happens. Now, if I consider this 3-dimensional representation, X, Y, Z, I have a hill If I consider the intersection of this hill with a plane parallel to the plane x and y, I will intersect this hill with, let me say, with this surface, characterized by this line and this line on the border. But if I do the projection of all this border of these lines here, I will obtain, let me show you, something like that, somehow, in the domain. If you want, I can show you in this form, something like that. But of course, if I consider a set of planes, I will have something like that, in which I can put here the level, I don't know, 3, 5, 6, let me say 6, which characterize the planes at different levels. This means this representation is equivalent to this one, but in 2 dimensions, in which this represent this z equals 3. If I consider another plane, a little bit higher, I will have at this level here, it could be 5. I don't know if I was able to clarify the concept of level curves. Level curves. This means, coming back to the presentation, then we will conclude for today, but I would like nevertheless to we have in the lower part of this picture all information which we have in the upper part, which we can see valley and we can see hills. What is these elements which are moving inside? They are particles which try to find a possible minimum or possible minima. It seems to be that from the animation that the majority find a possible minimum or maximum. Doesn't matter. That could be done in both. Let me see. Let me consider just a minimum. But we can see some elements is going in another minimum, but the majority seems to be localized one, or clearly localized one possible minimum. This means we have to conceive an algorithm starting from all possible domain or in a suitable domain relatively large in which we can see many minima, moving from the whole domain, they look, and then they will stop at the point in which they think that we have a possible global minimum. We can see that we have an exploration part in which the particle, they try to look everywhere, and then they concentrate in one, hopefully possible, just one region or the 2 regions in order to propose the solution which they found. Now, how we can conceive this kind of algorithm? I will present, and next week we will go in depth starting from here, just 2 minutes. But I would like to introduce these slides because it's the basic slide of all particle swarm optimization algorithm, PSO algorithm. And then we will see also how we can realize with the software, which look, and the swarm is characterized by a matrix. We can see a matrix X in which we have, let me say, n rows and d column, in which the idea of a swarm to be represented as a matrix is quite interesting. It's quite interesting because in a matrix with its row and column can be figured out in a swarm, in which the let me start with the row, probably is better. The rows represent the number of particles, birds, which are looking for the word, the number of particles which I am considering in the search. Of course, if I have more and more particles, more and more birds, the probability that I will find the best of the best, in math we say the global minimum, is higher. But the algorithm cost, because having a matrix with a lot of rows. Now, roughly speaking, the column domain represent the column, the number of the column represent the dimension of the domain. Here, the column is just 2, because we want to find the minimum in x characterized by x and y. Or if you look at this picture here, x1 and x2. Exactly what I told you before, omega and v. Or in my picture here, we want to find, for instance, here, this maximum. Again, maximum minimum is the same problem, and an optimum, characterized by x, y star, and x star. This point here is characterized by 2 coordinates, and this is Gymnasium, x star and y star. This means our swarm here is a matrix with 2 columns, because the columns represent the dimension of the problem. Dimension of the problem means the coordinates of my optimum. This means how many variables I have to find to obtain the optimum. The dimension, the number of the rows, better to say, is the number of elements which I use. I would like to conclude here. Just we will start next week trying to clarify this information here, which I didn't start now, not yet, but we can see that basically you have 2 equations. Just a few words, and then next week we will go in depth on this slide, and then we will switch in MATLAB directly. We have 2 equations, just a few words now. The last equation is the updated equation of the swarm. We can see it seems to be complex, but it's not. We have xi, comma j, which characterize the matrix. I don't know if you remember in math. The matrix is characterized by column, row, if you want, and column. I try to clarify the meaning of the row and the meaning of the column. Row is the number of particles which I am considering. The column, or the number of the column in general, is the dimension of the problem. How many parameters I have to consider to be optimized? X and Y, omega and V. But interesting, we have an index k, k plus 1 on the left equals x of k plus v of k plus 1, which is defined here. Here is the updated position of the particle, because basically it's the summation of 2 matrices. Let me show you so I can. Yeah, we can see here. I don't know how it's working here. Yeah. Zoom is really a problem total. Particularly if I have to do. Look, this summation here is an updated of the swarm, because the new position of the particles, this means the new matrix which characterizes the position of each particle, equals the old position plus an updated matrix. We can see it's in a matrix because it depends on I and J. I is the index of the row. This means the index which localize each particle, each bird, and y localize the dimension, or better to say, the parameter to be optimized. X and y, v and omega, and so on. About that, I will tell you next time, because basically we have 3 elements, but of course could be also more than 3. It depends I mean, we have many variations in this sense. Let me stop here. We will restart from this slide next time. And I will clarify, I will repeat again this slide. I will clarify in particular this expression here with respect, or with the help of this diagram here, which I am considering one particle which will look for a minimum, for instance, characterized by 2 coordinates, x1 and x2, v and omega, or x and y. And from here, we will directly consider the software, because these 2 equations conceptually, they are not so difficult. The program which realizes this conceptually is easy, but is quite articulated even in this basic form, because it's full of if, for, while loops, and this is a possibility for you to learn a little bit programming, because you told me you didn't do many programming, right? Many students don't have a background. It's not the goal now to learn really programming, but anyway, the basic knowledge about programming, I try to, through this example, to give you this basic knowledge about while loop, for loop. Did you hear about a little bit? While loop, for loop, if loop. Yeah, for you, for all students who doesn't know this knowledge is a little bit heavy, the lecture, but nevertheless, I will upload working files. And for a possible project in the context of optimization using this solver, solver means to find the minimum, to find or the maximum, could be nevertheless possible to modify this working file in order to solve your particular problem or the problems in your project. We will see next week at the same time. We have a lecture next week. It's not free, no? We have a lecture. With the PSO, I will dedicate the next week. It's probably also after next week, or the half of after next week. Yeah, I would like to say. In any case, next week, totally. And this is a good thing, because PSO is used a lot in engineering field, a lot, because it's extremely strong, easy to be understood. Also for today, we have seen this bird that is with the birds flying to find something. We will understand this abstract concept in the context of matrices, in the context of a program. I think it's a very important lecture, or the lectures, 2 lectures or 1.5, and then we will change the topic always in the context of optimization. Okay, if I have questions, I am here for answering your questions. Otherwise, next week, more or less, we will start always half past. No? Excuse me if I come a little bit later, but half past is now established. Basically, this schedule. I am here for you. Let me stop let me stop recording the lecture. Thank you for your attention. I am here, nevertheless, for your questions.